Hi everyone, and welcome back to Scaled Factory. In this new series, we are diving into the exciting world of thrust vectoring. Over three parts, I'll guide you through designing, printing, and testing a fully functional 3D printed thrust vectoring system. In today's video, we'll start with the heart of the system, designing the thrust vectoring gimbal in Fusion 360. I'll take you step by step through the modeling process to create a precise and efficient gimbal for the thrust vectoring. Whether you are a 3D printing enthusiast, a CAD designer, or just curious about thrust vectoring, this series has something for you. Let's jump into Fusion 360 and get started. We will create some parameters to define the diameter and the tolerance of the pin joint and the ball joint in the center. So we will be able to change the whole design by just changing these parameters. The first one is ball joint diameter. 50 millimeters is just working for me in this system. That's up to you. And the other one is the tolerances. These parts will be printed separately, so tolerances doesn't need to be really big, but still 0.4 is more than enough. Actually 0.2 you can use, but I will continue with 0.4. Now, the first component will be the pin component. The pin component has a spherical body on the top. So we are creating this one. We already defined it as a parameter. So we are using it here. It's 15 millimeter diameter. And it will be a basic rod that's connected to the sphere. Actually, in the final design, this rod will be connected to the body of the vehicle. 7.5 works for me, but it's up to you. As it gets smaller, it will be fragile. If it's too thick, there will be no movement place. And now another component. This will be the socket of the joint and also the motor mount. So we name it as motor mount. So motor mount itself will consist of two parts. The parts will, one side will be on the motor side, the other one will be the upper part. I'm using 28 millimeter diameter for motor mount because my BLDC motors has the same diameter with that thing, so 28 works for me. Again, it's up to you, it's your design. Now we will create the upper parts. Let's check the model from the side. The upper part should be high enough to hold the sphere, the pin of ball joint, but it shouldn't be more than enough. It shouldn't have more than enough height, so it won't limit the movement of the shafts of the pin part. So now I choose 6 millimeters. We can change it later if it won't work for us. And for the lower parts, so 10 millimeters works for me because the radius of the pin is 7.5 millimeters, and also you know that most of the BLDC motors has a small part on the bottom. The shaft is outside, so we don't want some interference. I just forget to make that subcomponents. Now I create upper part, and this body will go under it directly. Yep, because I want the two of them to be separate components. And now the lower part. 10 millimeters. Oh, sorry, not 19. 10, yes. So these two parts are now visible. Of course, there should be a hollow center of the motor mount, and the pin will be there. So now we will carve out this part. We are creating another sphere on the center, just like the pin. And now we will use the tolerance. Ball joint diameter plus ball joint tolerance. So it will be a little bit bigger than the ball joint, the pin side of the ball joint. It's better to always check what we are cutting. Looks okay. Let's check this hollow part. Yep, a spherical region where our pin will stay. Now let's go to another part. As we talked earlier, most of the BLDC motors has a small part of the shaft sticking out from their bottom. So it's better to have a hole here, so this part won't touch the motor mount. 1 centimeter in diameter is just enough for that kind of purposes. And we are cutting all the lower parts to the center. Okay, now it's time to put our fasteners, that small screws that hold the motor in place. In my BLDC motor, that servo screw holes are distributed around the circle. That circle has 16 millimeters in diameter. It may change, but in that sizes, most of the BLDC engines has similar diameter for that screw holes. Okay, let's create the holes, that screw holes that goes through upper and lower part of the motor mount. We want a simple hole type without threads. 18 millimeters in length is enough for us actually. And as long as we pass through the body, it's okay for us. It should be long enough. The head of the screw is about 5.5 millimeters, so 6 millimeters will work. And depth of the that head part of the screws. We choose 3, and our ones are metric 3 screws. So let's see our design. This part, that height of the head, may change, but it's better to have enough thickness of the upper part. So one hole is there. Now we will multiply it by using pattern, circular pattern. We can select all the faces, but first we should choose object areas faces. Then we can just use these icons. 4. We need 4 holes. Looks okay in preview. And now we have a problem. As you see, there's a small connection here. We can solve it by just making the upper part a little bit shorter. We can edit that extrusion process. Instead of 6, 5.5. Let's check if it works. Yep. For now it works. We will come to that small ridges later. Now we can insert the screws. Oops, not rivets, but bolts, round heads, and this one will work. Everything looks okay for us. And real nice of Fusion, it just knows where to put them. Okay, screws are in place. Here is the thing, you see, we should do something about the pin part because now uh, they intersect screw heads and the pin. For this, we will make cylindrical regions, that carved up regions around the pin. Now we will have a circle, the same diameter of ball joint, to have an intersection point with another perpendicular circle. Another circle. Oops, we chose the wrong point. Okay, once again. Let's hide the pin so it will be easier for us. Okay, here, but turned around on the axis. These circles will be the guide of our profile. Yep, let's see the pin again. And now cutting profiles. That intersection. The screw head was about less than 6 millimeters in diameter, so 7 will work for us. We'll use sweep to have a carve up the profile around the pin. Yep, we choose the profile. And our path is that perpendicular circle. So let's choose the region that we want to carve up. In upper part, we are carving all the way up. For lower part, we don't need it actually. Let's see it with the screws. So okay, that thing will work. Let's check the object we are cutting. Yep, only pin. Now, we delete the shaft too, so we'll create a new one without that carved out places. We multiply that hollow region with circular pattern. Everything looks fine. We can recreate the shaft. Again, it was 7.5 millimeters in diameter. The height is not important for now. We will choose it later when design is complete, but for now 25 or maybe a 30 millimeters looks okay. Okay, now the design looks like that. We can count that small ridges, edges here. We'll round them up by using fillet. .5 millimeter or maybe more actually. 1 millimeter looks way better. So our pin will have more movement angles. We can also soften that edges. I prefer first with chamfer to make the profile like that. Then I will use fillet to further smooth out these edges. Looks fine. I think the motor mount part is done. Now for pin, there are similar issues that sharp edges and points is hard to print. We'll choose all of them. Let me make it faster. Okay, we choose all the edges. Let's try it. Okay. 0.5. Let's try if it will work. Looks real nice. Okay, 0.5 millimeter. So pin looks ready too. Okay, it's our design for now. The central part, that truss vectoring gimbal. I strongly recommend to print this part first and check, because all the other parts of the design will based on this thing. So have it working, then proceed to other parts. That wraps up the first part of our truss vectoring series. We have designed the gimbal, which is a crucial component of the system. In the next video, we'll tackle the servo mounts and connections, bringing us closer to a fully functional system. Make sure to subscribe so you don't miss it, and feel free to leave any questions or thoughts in the comments below. If you found this video helpful, give it a thumbs up and share it with anyone interested in 3D printing or engineering projects. Thanks for watching, and I'll see you in part 2.